confidence interval for the mean. So we have a sample of n equal 15 patients. The mean creatine level x bar 1.4 milligrams per deciliter. A population of all potential patients. Creatine is normally distributed with unknown mean, but with known standard deviation 0.5 milligrams per deciliter. So that's sigma. So we want to find a 95% confidence interval for the mean. So we want to find two values such that we're pretty sure the unknown population mean is between those two values. The sample mean is actually a point estimate, for the population mean. Our best guess as to the population mean is the same as the sample mean, which is 1.4 milligrams per deciliter. But that could have happened by chance, and so we want an interval where we're pretty sure that the exact mean falls within that interval. So our confidence level, 95%, or as a decimal is 0.95. And some of the exercises in WebAssign, they'll ask you to fill in label a graph like this. They want to fill in the label. So CL, confidence level, 0.95. The alpha over 2, our level of doubt is 5%. So 100% minus 95% is 5%. That's our level of doubt. That's also called the level of significance, and that's represented by the Greek letter alpha. So alpha over 2 is 0.05 divided by 2 is 0.025, and we put half of our doubt at each of the two extremes. So the desired confidence is in the middle. That's 1 minus alpha. That's 0.95, and then we would put a half of our doubt at the two extremes. So we want to use the z-table in reverse, and so 1 minus alpha is our level of confidence. Divide that by 2, 0.95 divided by 2 is 0.475. So we look in the z-table for 0.4750 in the z-table, and it's in row 1.9, column 6 in the z-table. The z value that goes here is 1.96, and if you use the table in the Canvas, in the course files in Canvas, it's a one-page table. It doesn't give the negative z scores, but on this side we'll have a negative 1.96. Okay, so and then we want to find the x scores that go with those z scores. So so we want to find these x scores. So there's a formula for that we can plug into. So the lower bound is going to be x bar minus whatever's in the table times standard deviation divided by the square root of n. So that's going to be x bar is 1.4 minus 1.96. Sigma is 0.5, and divided by square root of n, which is square root of 15. I'm going to do what's after the minus sign separately, because sometimes that is reported separately. 1.96 times 0.5 divided by second square root 15.253. And if we do the subtraction, we're going to get, I'm going to store this in memory. .14. 69650 0.88. This is approximately 1.15. And that's milligram per deciliter. Okay. This number that we're subtracting, I computed that separately because this is the margin of error. Sometimes it's called the error bound. This piece here, margin of error or the error bound, that's sometimes reported separately. Then the upper bound is going to be the same expression, but it's going to have a minus sign in it. So it's going to be 1.4, and it's going to have a plus sign instead of a minus sign, plus 1.96 times 0.5 divided by square root of 15, 1.4 plus 0.253, 0.34912, and that's going to be 1.653, 0.34912, approximately 1.65 milligrams per deciliter. Okay, and we see have the same margin of error occurs here. This is the margin of error again, or the error bound, so that means we're 95% confident that the mean of the entire population of patients, mean creatine level is between 1.15 and 1.65 milligrams per deciliter. The error bound, margin of error bound, sometimes denoted E or EBM, is approximately 0.25 milligrams per deciliter. That's how far off we can expect to be. So the 1.4 is a point estimate for the unknown population mean mu, but now we have an interval where we're 95% confident that mu is somewhere between 1.15 and 1.65 milligrams per deciliter. Okay, so according to the Central Limit Theorem, confidence interval formulas for the mean are valid if the population standard deviation is known and either n is at least 30 or the variable is normal. So this formula is based on the Central Limit Theorem. The standard of n greater than or equal to 30 is arbitrary. Some books use different standards. Our book uses at least 30, but the larger the sample size is, the closer these values will be. Okay. Okay, so again, the x bar is a point estimate for the unknown population mean mu. Sample will vary from one sample to another, but on the average will equal to the unknown population mean. The 95% confidence interval, 1.5 to 1.65, is an interval estimate, and the confidence interval will vary from one sample to another, but 95% of the time will contain the unknown population mean. The margin of error, 0.25, also called the error bound, or the sampling error, or just error, within plus or minus, tells us how far our point estimate can vary with 95% confidence from the unknown population mean. A good but possibly expensive way to decrease the margin of error is to increase the sample size. A cheaper way of decreasing the margin of error is to decrease our desired level of confidence. But there's trade-offs regardless of trade-offs. So if you want a more precise estimate for the population mean, the bottom line is you need to put out the money for a larger sample. Okay, example 2, standard deviation for lung capacity is 0.4 liters. Researchers wish to determine mean lung capacity in liters with 97% confidence and margin of error or error bound of less than 0.1 liters. Okay, so I think I looks like, to me, looks like I'm frozen here. But, okay, now I'm unfrozen. Okay, so so we want to know how large the sample size should be. So before you do a study, it's helpful to know how large the sample size should be, because again, large samples are expensive, but they're going to tell you, they're going to give you more precise information than a smaller sample would be. So there's a trade-off involved. So so this is, before we're doing the study, let's see how big a sample we want. We want 97% confidence. We want to be off by less than 0.1 liters. Again, in Web of Science, they often ask you to fill in the blanks here. The confidence level, 0.97. That's 1 minus alpha. Alpha is the level of doubt. It's actually the level of significance. I think level of doubt is more descriptive, I think, but it's represented by the Greek letter alpha. Alpha divided by 2 is 0.03. We have 3% doubt, 97% confidence. 100 minus 97 is 3% doubt. 0.03 divided by 2 is 0.015, so that's alpha over 2, 0.05. So we want to use the z-table in reverse. So our table, with the one-page table, we want to divide the confidence by 2. 0.97 divided by 2 is 0.485, and look for 4.485 in the body of the z-table. It's in row 2.1, column 7. So it's 2.1, column 7. So the z-score is going to be 2.17, and on this end it will be negative 2.17. So we want to let me just do this from using our previous formula. So if we look at our previous formula, the margin of error is what comes after the plus or minus sign here. So we want z 1 minus alpha over 2 sigma over square root n be less than, we want the margin of error to be less than 0.03. So we want this expression here to be less than 0.03, because our desired confidence is 97%, so our desired margin of error has to be 3% or 0.03. No, our desired margin of error is 0.1 rather, 0.1. Our desired margin of error is 0.1. So we want the error to be less than 0.1. So the z-score is 2.17. Sigma, they said, was 0.4. And n is what we're trying to find out. So if we solve this for n, well, let's simplify this as 2.17 times 0.4 is 0.868. Less than 0.1. And if we multiply both sides by root n, that means that 0.868 root n over root n less than 0.1 root n. And we can cancel the root n's on both sides. and that gives us 0.868 less than 0.1 root n. Divide both sides by 0.1. 8.68 less than root n. The 0.1s will cancel. And then square both sides. So now we want to square both sides. Square and the square root will cancel. And it gives 8.68. Uh, 75.3424. That means that n has to be greater than 75.3424. And sample size has to be a whole number. You're not going to be able to sample a fraction of a person. 75 is not going to give us our desired margin of error. 76 is a little bit bigger than what we need, but it's better to overestimate than underestimate. So we want n to be at least 76. Let's say patients, at least 76 patients. Okay, so that concludes this presentation.